Hello student, I am Professor Jayant Chopde, working in Electronics and Telecommunication Department. I would like to welcome to this lecture on elementary continuous time and discrete time signals. Now in previous lecture we have studied the classification of the signals, and in that we discuss the deterministic signals and non-deterministic signal. Non-deterministic signal is also called as the random signal. Then the energy signals and the power signals, and the last one is the even signals and the odd signals. Now in this lecture we are going to discuss the basic continuous time and the discrete time signals. And the basic signals are the step signals, ramp signals, impulse signal, rectangular pulse function or the signal, signum function, sinc function, and the complex exponential signals. Now what are the basic continuous time and the discrete time signals? The basic signals are the step signal, ramp signal, sinusoidal signals, and the exponential signals. And what is the signal modeling? Signal modeling means the representation of the signal using the mathematical equation or the expression. Now if we say the sine waves, the sine wave is written in mathematical equation like this: x of t that equal to a sine of omega t plus phi. Now here this expression is called as the signal modeling. Now the first basic signals is the step signals. Now the step signal is generally mathematically is represented like this: ut that equal to a when t is greater than or equal to 0, and the value of the signal is 0 for the negative value of t. Now the example of the step signals is, now when we turn the ignition key of a car, we actually introducing the step voltage to starting a motor. The second example is when we apply the brake to an automobile. We are applying a constant force, and that constant force is nothing but the step signal. Now here this figure shows the unit step signal. When we will say this one is unit step signal, when a equal to 1, when the amplitude of that signal is 1, that signal is called the unit step signal. And the signal modeling for the unit step signal is like this: ut equal to 1 for t is greater than or equal to 0. Now see, observe this figure. For t is greater than or equal to 0, the amplitude is 1. Otherwise, this amplitude of the signal is 0. Means for the negative value of the t, this signal is 0. Then the discrete time unit step signal. As we know the difference between the continuous time signal and the discrete time signal. The discrete time signals is occur at the discrete instances of time. Means this is n equal to 1, 2, 3. Now here this mathematical equation for this discrete time unit step signal means this signal is 1. Here this is 1 for n equal to 1, n equal to 2, n equal to 3 up to infinity, means for the positive value of n. And for the negative value of n, the signal magnitude or the amplitude becomes 0. Means we can say that unit step signal is occur only for the positive value of t or the positive value of n. Then the ramp signal and the unit ramp signal. This ramp signal is expressed as like this: a t for t is great a by t for t is greater than or equal to 0. And when a and t both value, means this slope of this line the magnitude is a and this duration is t. Then if we find out the slope of this line, the slope of this line is a by t. And t means we can say that this ramp signal is continuously increasing with respect to time as t is increasing for the positive value of t when t is greater than or equal to 0. And when the slope becomes 1, means when this is a equal to 1 and t equal to 1, that time the slope becomes 0, means a by t becomes 0. Sorry, a by t becomes 1, not 0, because the slope of this line is 1. Then this signal is called as the unit ramp signal. Then the discrete time unit ramp function or the signal is denoted like this: ramp n that equal to n for n is greater than or equal to 0, and this is 0 for n is less than 0, means for negative value of n, means for 0 this value is 0, for 1 this value is 1, for 2 2 3 3 4 5 like this. This signal is called as the ramp signal, and the ramp signal is obtained by integrating this unit step signal. If we integrate, this is integrator circuit, and the input for this integrator circuit is unit step signal, that is previous signal. The output is the ramp signal. This is 1 t rt. As we know that the integration of 1 dt that equal to t, and t is nothing but the ramp signal. The next one is the parabolic signal. Now if we integrate the ramp signal, we are getting this another signal, and that signal is called as the parabolic signal. Integrate, this is integrator circuit, and output is here parabolic signal. Means integration of t into dt, this is t. Mathematically this ramp signal is represented by t, and if we take the integration of this is t square by 2. Now if this slope of this line is 1, then that signal is unit ramp signal, and if that signal is applied to the integrator, that signal becomes the unit parabolic signal. Means here the a value becomes 1. And the nature of this parabolic signal is like this: this is t and this is signal. For 1, this is 1 square by 2, means this is 0.5 this. For 2, if we take 2, t equal to 2, 2 square divided by 2, means this is 4. For 4 divided by 2, means this value becomes 2. For 3 square divided by 2 means 9.9 by 2, that is 4.5, means for 3 the function or the signal is value is 3.5 like this. Then the relation between unit step signal, unit ramp signal and unit parabolic signal. As we discussed, the ramp signal is obtained by integrating this unit step signal, And the parabolic signal is obtained by integrating the ramp signal, that is t square by 2 unit ramp signal. Similarly, unit step signal is obtained by the differentiating the unit ramp signal. Means if we, this is unit step signal, if we integrate this, we are getting the ramp signal. And if we again integrate this, we are getting parabolic signal. Similarly, if we differentiate this ramp signal, differentiation of this ramp signal, that equal to unit step signal. Reverse differentiation of ramp signal, that equal to 1. T, differentiation of t is 1, means that is the unit step function. Similarly, if we differentiate the parabolic signal, that time we are getting the ramp signal. Then next one is the impulse signal. Now this impulse signals is important signal in the signal analysis. The impulse function is also called as the delta function, and the signal is used to measure a spike that occur in one instant of time. Now here we will define this impulse signal. What is the impulse signal? Now consider this rectangular pulse, and using the rectangular pulse we will study the approach as an impulse signal, or we will study the impulse signal. And the area of this rectangular pulse is 1. Consider this. Means if the height, we know that for the rectangular pulse, what is the area? Area is nothing but height into width. Means if the height is 1 by a, means width should be a. Area is 1. Now, if we decrease the duration of the pulse, now its amplitude will be increased, and the area remain same. Means by the same amount decrease the width, so that this by same amount the height will be increased, and due to that the area will remain same. Again decrease the width of that signal, height will be more. Decrease width, height will be more, and area remain same. Now the more you decrease the duration, the closer the rectangular pulse comes to the impulse function. Mean the instant where the time is very small, mean that is infinitely thin in time, or theoretically we will say that time is 0, means the amplitude of that signal should be infinitely large, or that theoretically that should be at infinity, and the area under that curve remain same, and that area is 1. And this signal is exist only at t equal to 0, because we are decreasing the width of that rectangular pulse, and at t equal to 0 that signal will becomes impulse signal. And due to that the impulse signal or the delta signal is represent like this: delta t equal to 1 when t equal to 0, as the signal exists at t equal to 0. Otherwise the value of that signal is 0. And the second important thing is the area under the curve, minus infinity to plus infinity. Area of that impulse function, impulse signal is 1. Now this is graphical representation of the impulse signal. As the signal is exist at 1, and this arrow is indicate that the amplitude is very high, infinitely large in amplitude, and width is narrow, and the area of this signal is 1. Now this is the shifted signal, shifted on this right hand side by this time amount tau, and that time the signal is denoted by t minus tau. Now the signal is, this is shifted signal, the signal will exist only at t equal to tau. Otherwise the signal becomes 0. Similarly, in discrete time, the signal is represented like this. This equal to 1 for n equal to 0, and for all others value, this becomes 0. Then the important point of these impulse signals are, first is impulse is 0 everywhere except at origin or at t equal to 0. And the total area under the unit impulse signal is unity, that is 1. Now some physical phenomena that we observe, that are the example of these impulse signals. First one is the lightning. The lightning has a lot of energy and occurs in a short amount of time. And that fit the description of the impulse function, as we know that the impulse function is occur at t equal to 0, having the width is very small and the height is infinity. Now here this energy occur, means lot of energy is there in a short amount of time in lightning. We can view the impulse as the derivative of the step function. As we know that the step function is t, and if we take the derivative of this, mean this is constant, but there is the abrupt change from 0 to 1 for the unit step function at t equal to 0. Hence if we take the differentiation of this, we are getting this is spike having this time period is very small, and after this, as amplitude is constant and the differentiation of the constant becomes 0. Mean this is the signal, and that signal is having the impulse signal nature. Then the important property of the unit impulse function. Now assume that x of t is a continuous function. This is x of t is the continuous function at t equal to 0, 1, 2. And then the another function, that is the delta function. This second delta function is multiplied to this, and the delta function is exist at t equal to 0. Means for this positive value of t, this multiplication becomes 0, and for the negative value 0. Means we are getting this signals value only here. This means this becomes x of 0. Means we can write here x of t into del t, that equal to x of 0. Now this one is the shifted function. For the shifted function, mean this is x of t, and this signal is shifted by t0 amount, Now this will exit at this instant, del t minus t0. Now the multiplication of these two will be occur only at t0. Means this becomes x of t0. Means we will write here x of t into del t minus t0, that equal to x of t0 into del t minus t0. Now if we substitute this value in this integration, then we are getting this integration minus infinity to plus infinity. Now instead of x of t, now this become x of t0 and del t minus t0 dt. Now as the integration is with respect to t0, this t0 integration is with respect to t, the x of t0 is constant with respect to t. Hence we will take the outside the integration, integrate this. Now area under the delta function or the impulse function is 1. Means we will say that minus infinity to plus infinity del t minus t0, that equal to 1. And this becomes x t0 into 1. Means the integration of this term, that equal to x of t0. Another property is this, fourth property, this is minus infinity to plus infinity x of t del t. Now we know that x of t and del t, that equal to, in previous slide we studied this, that equal to x of 0, as the delta function is exist only at t equal to 0. Hence we will write this for this. Then minus infinity to plus infinity x of t, this becomes x0 into del t dt. We will solve this minus infinity to plus infinity x0. Now as integration is with respect to t, x0 is constant, and this is outside this integration, x0 del t dt. What is integration of this? Integration of this term is 1, because the area under the curve of this impulse signal, and that equal to 1. Hence we will write this x of 0 into 1, and that equal to x of 0. Means if we multiply this signal with the delta function at origin, that time we are getting that function only at t equal to 0. Similarly, this is x of tau del t minus tau d tau, this integration of this, and that equal to xt. And this is called the convolution integration, and we will discuss this convolution integration in next unit. Now here this multiplying this function independent variable to some constant value. Means if this delta function multiplied by del at, that equal to 1 upon del a del t, this property. Then the rectangular pulse function. Rectangular pulse function is also called as the gate function. That function is occur only the particular duration of time with the same amplitude. Hence this rectangular function is also represented by this. Means this is the gate, the duration is fixed, time duration, that t equal to RECT, rectangular function, and that equal to a a rectangular t by tau, where the tau is the duration. If this is minus tau by 2 to plus tau by 2, then the duration is this tau by 2 minus tau by 2, means that equal to tau. That duration is this tau. As this is the function of time, this is t, and the amplitude of this rectangular function is a. If the amplitude of this rectangular function is a, then mathematically the rectangular function is represented like this and graphically like this. And when the amplitude a becomes 1, that is called as unit rectangular pulse function, means for the particular duration from minus tau by 2 to plus tau by 2, the amplitude of that function is 1. And this dt signal is also represented as the rectangular n, where n is discrete interval of time 0, 1, 2, 3, 4, and this capital N is the duration of that sequence. Means if this sequence is from minus n by 2 to plus n by 2, then the total duration of this sequence is n. And the graphical representation of the rectangular pulse function in discrete domain is like this. Then triangular pulse function. The triangular gate function is denoted by del a t, where a is the duration of this pulse function. Now if we consider here, this is increasing, this is decreasing, and where the rising edge and falling edge for both edges, if the slope is same, that function is called as the rectangular function, and it is pulse. This is not continuously increasing and decreasing, it is pulse, and this is called a rectangular pulse function. Now mathematically the signal is represented like this. Means the mathematical modeling for the triangular pulse function is 1 minus mod of t divided by a for the duration from minus a to plus a. This mod of t means this is positive value or negative value. And when the signal is greater than a, for positive value or for negative value, the amplitude becomes 0. Now we will find out this slope of this signal to represent the signal in mathematical equation. Now for this line, first this amplitude is 1 and this is a, means the x coordinate is a and y coordinate is 0 for this point. And for this, the x coordinate is 0 and y coordinate is 1. And this is the line intersecting this y-axis at 1. And we know that if we consider this is the x-axis and this is y-axis, the equation of this line y equal to mx plus c. Now what is m? M equal to the slope of this line. And what is c? C is nothing but the intersection of this line to the y-axis. Then m is y2 minus y1 divided by x2 minus x1. What is y2 here? 1 minus 0 divided by 0 minus a. Means slope of this line is minus 1 by a. And the intersection, by observing this, we can say that the intersection for this line is 1, or you can find out this by substituting this x equal to a and this 0 value, find out the intersection, we are getting the same value, that is c. Means for this we will write this equation of this line, and this x-axis is the time domain axis. M is slope minus 1 by a, and the intersection is 1, and into t, mx, x is t. Means after simplifying this equation, we are getting this is 1 minus 1 by a t. Means for the positive value of t, this is 1 minus t by a, and for the negative value of this, the slope becomes plus, and this is minus minus, that becomes plus, minus t, and this minus sign, that becomes plus. Means for this line, the equation is like this. Similarly, for this part, the slope of this line, find out the slope of this line, that is 1 by a. Means the equation is, and the intersection c is 1 by observing this. Then y equal to mx plus c. M is 1 by a. Here x value is t, and c is plus 1. Means this is 1 plus 1 by a t. Means if you substitute this negative value t, this minus minus becomes plus 1. Means this is for the negative value of this t, equation of this triangular wave, and this is for the positive value of this t. Then next one is the signum function, and the signum function is defined as the amplitude of this function is 1 for t is greater than or greater than 0, and this value is 0, that is plus 1 and minus 1, that value is 0 at t equal to 0, and this value becomes 1 for t is less than 0. This becomes minus 1. And this graphical representation of this function is like this. For t is greater than 0, this is positive and the magnitude is 1, and for the for negative value of t, this value is minus 1. Now this function can be expressed in terms of the unit step function, that signum t equal to 2 ut minus 1. As we know that the ut function, means the unit step function, is exist only for the positive value of t. Hence for the positive value of t, for this ut is 1. Means this function becomes, or we will write here, for positive value of this t, this is 1, 2 into 1 minus 1, means this becomes 1, as this function is exist only for t is greater than or equal to 0. And for the negative value of 0, this is 0, means for this signum function, that equal to minus 1. Means we can write the signum function in terms of unit step function like this, or if we simplify this equation, we will write the unit step function in terms of the signum function. Then the next function is the sinc function. Now mathematically, the sinc function is defined as sinc pi t divided by pi t, or sine t divided by t, and this function is exist from minus infinity to plus infinity, and mainly this function is used in the communication system, that is in the Fourier transform. And this representation of the sinc function is like this. This image shows the representation of this sinc function, and generally the signal modeling for the sinc function is like this. Now if we observe this waveform for the sinc function, then we will define this sinc function at t equal to 0, means we will find out this value for the sinc function at t equal to 0 at this instant where this sinc function is minimum, and here after this sinc function is maximum. And a is the a tau, and here the tau is the duration from the 0 to first lobe crossing to this tip, and the duration is denoted by tau. Now at t equal to 0, as we know that the sinc function is sine pi t tau divided by pi t tau, and if we substitute t equal to 0, then the sine 0 is 0 divided by this 0, mean this is the 0 by 0, mean this is indeterminate form. Hence we cannot find out the value of this function at t equal to 0 directly. Hence we will use the L'Hospital rule, that is differentiate this numerator, differentiate denominator, and substitute this limit t tends to 0. And if we differentiate this numerator, that is differentiation of sine is cos pi t tau into differentiation of this term, that is pi t tau is pi tau, divided by differentiation of this denominator is pi tau. This pi tau cancel out, and this is a tau cos of this, and if you substitute this is 0, t equal to 0 means that becomes cos 0, and this cos 0 is 1. Hence this amplitude of the sinc function at t equal to 0 is a tau. This is a tau. Then find out this maxima and the minimas. The minimas of the sinc function is the value where this function becomes 0. This value we will find out. Means the sinc function is a tau divided by sine pi t tau divided by pi t tau, that equal to 0. We will equate this function equal to 0. And this pi t tau, if we multiply by this function into 0, means that becomes 0. Now here this is a tau, again that becomes 0, as this 0 divided by a tau. Means the remaining term is only the sine pi tau t, that equal to 0, and this is the sine function. And when the sine function is become 0, the sine function becomes 0 at pi, 2 pi, 3 pi. Means in general we will write this is plus minus n pi. Similarly for this negative side also, this is minus pi, minus 2 pi, this is plus minus n pi. Means t equal to plus minus n pi divided by pi tau. This pi will cancel out, and that is n at tau. When n equal to 1, this is 1 by tau. See here, this function at t equal to 0, this is a tau, and this minimas are first for n equal to 1, this is 1 by tau. For negative side, that is minus 1 by tau. When n equal to 2, this is 2 by tau. Similarly here this is minus 2 by tau. Then the maximas, this maximum value of this sine function is 1. Hence we will equate this equal to 1, and when this is 1, this sine function is 1 at pi by 2, and the multiple of this means 3 pi by 2 like this. Means we will write this is 2n plus 1 pi by 2. When n equal to 0, this is pi by 2. But when n equal to 1, this is 3 pi by 2. Then for n equal to 2, this is 5 pi by 2 like this. Means after solving this, we are getting this t equal to 2n plus 1 divided by 2 tau. This. And if we substitute here n equal to 1, this pi cancel out and t equal, this tau comes here and this 2, n equal to 1, then this is 5 by 2 tau. N equal to 1 means this is 2 into 1, sorry, 2 into 1 is 2 plus 1 divided by 2 tau, means this is 3 2 by tau, means that comes 1.5 by tau. Similarly on this side. And if you observe this signal is the even function. It is a even function of t. Then this complex exponential signal or complex signal. Now here there are two types of these signals. First one is the real exponential signal and second one is the complex exponential signal. Now first the real exponential signal. The real exponential signal is denoted or defined like this: c into e raised to at, where this capital C and the small a both are the constant and are real. Now here when a equal to 0, for the different value of this small a, we are getting the different signals and the nature of that signals are the different. Now when a equal to 0, then this is c e raised to 0 and e raised to 0 is 1, means into c into 1, means this is c into 1, that equal to c. Means here we are getting this constant value. A equal to 0, the signal is the DC signal or the constant value. When c is greater than 0, means this is positive value, and when a is greater than 0, that time the nature of the signal x of t, that equal to c into e raised to a t. Now this is greater than 0, means for 1, for this is, we will consider this a equal to 2, means 2 into t. As t is increasing, this value is increasing, and at t equal to infinity, this value becomes, the signal becomes infinity. Means we can say that at t equal to infinity, signal becomes infinity and the signal is the growing exponentially. And at t equal to minus infinity, this is e into 2 into minus infinity, means that is e raised to minus infinity 1 upon e raised to infinity, means this becomes 0. Means this is for minus infinity the signal is 0 and for plus infinity the signal is infinity, means this is the growing signal. Similarly for a equal to, a is less than a, less than 0, a is less than 0, means this for the negative value of this a, the signal is e raised to minus at. And for positive value of this t, this is e raised to minus infinity and that is 0. And for negative, this is minus infinity and this minus means at t tends to minus infinity, the signal is e raised to minus a into minus infinity. This is a and this is become e raised to infinity. Means at t equal to minus infinity, the signal is infinity, and as t is increasing and that is approaches to infinity, that signal becomes 0. Means this nature of the signal is called a decaying exponential. This is decreasing signal, exponentially decreasing signal. Then the complex exponential signal. The most general form of the complex exponential signal is e raised to st, where s is the complex plane or also called as the complex variable, and this complex variable is consist of two parts, sigma plus j omega. Sigma is called as the real part of this complex plane and j omega is the imaginary part of this complex plane. Now if we substitute s equal to sigma plus j omega in equation 1, then we are getting this is e raised to st, that equal to e raised to sigma plus j omega t, that is e raised to sigma t into e raised to j omega t. This is equation number 2. We know the Euler's identity e raised to j omega t. This complex term is represented in terms of the sinusoidal signal, that is in terms of cos and sine, and that equal to e raised to j omega t, that equal to cos of omega t plus j sine of omega t. Now substitute this value in this equation. We are getting this value, equation 3 in 2, we are getting this equation. Now depending on the value of sigma and this omega, we get different signal. Now first case, when sigma is 0 and omega is 0, means this term is 0, this is 1, that time this term becomes e raised to sigma t, cos of 0 is 1 plus 0 means e raised to sigma t multiplied by 1 means this term. Now here sigma is 0, means this is e raised to 0, then we are getting the DC signal. This is one value. If sigma is 0 and omega is 0, that time we are getting the DC signal. And if omega is 0 and sigma is not 0, that time we are getting the exponential signal, and that exponential signal is either increasing or decreasing, that we have studied in previous slide. That is the real exponential signal. When sigma is greater than 0, this is exponential growing signal, and when the sigma is less than 0, this is the exponential decreasing signal. This. And the third case, when sigma is 0 and omega is plus minus j omega, that time we are getting this sinusoidal signal with phi equal to 0, means this is sine wave. Now when the sigma is less than 0 and omega is finite, means this is e raised to sigma t, less than 0 means this is negative value, and due to the finite we are getting this sinusoidal waveform. Now we will find out here this e raised to minus sigma, and for minus infinity this is e raised to infinity, means at minus infinity this value is infinity, and for t is infinity, at t equal to infinity, now this value becomes e raised to minus sigma into infinity, and this is e raised to minus infinity, that is 1 upon e raised to infinity. So 1 upon infinity means that is 0. Here as t approaches to infinity this value will be approaches to 0, and this is the sinusoidal waveform, and this nature of this waveform is decaying the sinusoidal signal as this amplitude is decreasing. Similarly, for the sigma is greater than 0 and with finite omega, and using the same concept here e raised to sigma t, now this is positive at t equal to minus infinity, this is e raised to minus infinity into sigma positive, mean that is e raised to minus infinity, mean that is 0, and at t tends to infinity this value becomes infinity, e raised to infinity, because this is now positive, sigma is positive, t is positive, and that is infinity, e raised to infinity is infinity, means as t approaches to infinity this signal is infinite, this is continuously increasing, and hence this signal is called as exponential growing sinusoidal signals. Now this is the assignment based on this lecture. Find whether the unit step signal is power signal and or an energy signal, and the answer for these examples is given here. You solve this assignment. Now in this lecture we study the basic, that is also called as standard or also called as elementary signals, and the importance of these basic signals, because these signals are the basic building blocks for the complex signals. And in that we studied the unit step signal, ramp signal, and the impulse signals. And the impulse signal is very useful signal to analyze this signal analysis. Then rectangular signals, triangular signals, sync signals, and signum signals, and in the last real exponential signal and the complex exponential signals. Okay, we stop here.